Very good morning to all of you. In the last class, we discussed some problems in electrostatics. We looked at forces on charges, etc. Today, what I am going to do is to discuss some problems in the field of using magnetic fields. So, we will continue with our discussion on problems. So, I will discuss today problems in magnetic fields. So, let us look at the first question. Consider a vector field given by f is equal to k x I cap plus k y j cap, where k is a constant. Can this vector field represent a magnetic field? So, we have a vector field given by f is equal to k x I cap plus k y j cap, and the problem is to find out whether such a field can represent a magnetic field. Now, what do we know about properties of magnetic fields? We know that magnetic fields must satisfy an equation which is essentially says that integral b dot dl b dot dA must be 0. That is, the flux of magnetic field from any closed surface must be 0. So, we need to check whether this particular field satisfies this condition. Now, as before, I can take any arbitrary surface, any arbitrary closed surface, and calculate the value of integral f dot dA and check whether it happens to be 0. Now, for simplicity, I would like to take a surface which will help me to evaluate these integrals easily. So, here is the surface which I will take. Here are my coordinates. This is x, y and z. So, let me take a cube here. So, I have so cube of side A, and this is the origin here. So, these are now there are 6 surfaces here. This is one surface here. So, let me call this surfaces by names. So, this one I call S1. So, this is 1, this is 2, this is 3 and this is 4 at the bottom, and then 5 is this one, the front surface, this is 5 and the back surface is 6 surfaces. So, what I need to do is to calculate the value of integral b dot dA over this closed surface. So, I will have to integrate this over all these surfaces to check whether I satisfy this equation. So, let us start with the first surface. So, total integral b dot dA is equal to integral b dot dA over S1 plus integral b dot dA over S2 plus integral b dot dA over S3 plus integral b dot dA over S4 and similarly integral b dot dA over S5 and S6. Okay, so, I need to calculate each of these integrals and check whether the sum is equal to 0. So, let us start with integral b dot dA over S1, integral b dot dA over S1. So, let me redraw the figure here. So, remember this is the cube in which I am integrating. So, this is S1, this is x, y and z. So, what is dA for this? dA will be equal to, it is an area which is the normal to this area is pointed along the x direction. This is the normal. So, the area vector will be, and this surface is parallel to the y z axis. So, dA will be dy dz into I cap, and B is given by k x I plus k by j cap. So, B dot dA on this surface. So, this distance being A, first of all this is equal to, this is k x I plus k by j at x is equal to A dot I into dx dy dz. So, this is nothing but k A, I have to substitute x is equal to A and j dot I is 0. So, k A dy dz. So, integral B dot dA over S1, which is equal to integral k A dy dz over S1, which is equal to k A times integral dy dz over S1, and dy dz over S1 is nothing but the area of this flat surface, which is nothing but A square. So, I get k times A cube. So, that is the flux of magnetic field crossing the surface S1 is k A cube for this given magnetic field. Similarly, I can calculate the flux through all other surfaces. So, for example, let me just calculate one more surface, which is S2. So, let me calculate from S2. So, integral B dot dA over S2. So, again I draw the figure here. So, S2 is the top surface. So, this is the normal x, y, z. So, what is dA here? dA will be equal to, now this surface is oriented, the area is along y cap. So, this is j cap and it will be dx dz, dx dz j cap, and B is equal to k x I cap plus k by j cap. So, B dot dA on surface S2 will be equal to, now this surface S2 y is equal to A. So, and I dot j is 0, j dot j is 1 and y is happens to be A, because this distance is A. So, this is nothing but k A dx dz. So, integral over S2 B dot dA is equal to integral k A dx dz over S2, which is equal to k A times integral dx dz over S2. What is S2? This is the area, and d by dx dz is nothing but the area, which happens to be a square. So, this is k A cube again. So, I have evaluated over surface S1 and S2. So, I would like you to continue the discussion and evaluate all other integrals. So, let me just give you the values here. Over S3 B dot dA will be equal to 0, over S4 B dot dA will be 0, over S5 B dot dA will be 0, and over S6 B dot dA will be 0. So, integral B dot dA happens to be equal to, it has only contribution from two surfaces S1 and S2, and that is so I get 2 k times A cube, and this is not equal to 0. So, hence F cannot represent a magnetic field. So, this particular vector field which I wrote as in the question, this particular vector field cannot represent a magnetic field, because integral B dot dA of this vector field is not 0 over a closed surface. So, please remember, just like not all vector fields can represent electric fields, not all vector fields will represent magnetic fields. So, they have to satisfy certain properties to be able to represent an electric field or a magnetic field. Now, let me look at another question here. So, calculate the magnetic field produced by a finite current element as shown. So, I have an element of current. So, this current is I here, and I want to calculate the magnetic field at some point P here due to this current element. So, the problem is I have now a certain current element, and I want to calculate what is the magnetic field produced by this current element at this point. Now, obviously, this current element cannot exist independently, but in many circuits you will have many straight sections, and for each section I can actually individually calculate the magnetic field, and so from there evaluate the total magnetic field from there. So, I would like to evaluate this. So, for this what I do is the following: I take a small element of length here. So, let me call this direction this as z axis, and let me call this distance as r from here. So, I take a small element and join these 2 points. So, this is the small current element which I will call I dl, and this distance, this vector I call s vector, and let me call this angle as theta. So, I calculate what is the magnetic field produced by this small current element at this point and integrate over all elements from this point to this point to get the total magnetic field. And the magnetic field produced by this small current element dB will be equal to mu naught by 4 pi I dl cross s by s cube. Please remember, this we had discussed earlier in Biot-Savart law. The magnetic field produced by the small current element dl vector at this point will be I dl cross s by s cube into mu naught I by 4 pi. So, and the total magnetic field will be obtained by integrating. Now, first thing that we must notice is that dl cross s. So, dl vector is pointing upward, s vector is pointing here. So, dl cross s is pointing inwards. So, the magnetic field produced by this is pointing into the paper, and all current elements from here to here, all these current elements have a magnetic field which are pointing into the paper here. So, each current element in this length will produce a magnetic field which are all pointing inwards, and that helps me to sum up all the magnetic field components. So, the total magnetic field I will calculate by integrating from this point. So, let me call this Z1 and coordinate of this is Z2. So, Z1 is this distance and Z2 is the distance of this point from this point. So, this is actually a norm which I have drawn from here. So, this is my current element. I need to calculate the magnetic field here. I drop a perpendicular on this line, that distance is small r, and Z1 is the coordinate of the bottom end of the element, Z2 is the coordinate of the top of the element, and I have defined the angle theta. So, now what is dl cross r? Dl cross s. So, dl cross s, which is equal to, so dl cross s, if theta is this angle, I will have dl s sin theta. Now, what is theta? Theta is here, if I call this alpha, then sin theta is nothing but cos alpha. So, this triangle you can actually find out that sin theta is nothing but cos alpha, and so I get dl cross s is equal to dl s cos alpha, and s square is equal to, now what is s? The length of this length from here to here, s square is r square plus z squares. So, this has a coordinate, I am assuming as a coordinate z. So, s square is equal to r square plus z square. So, dB magnitude is nothing but mu naught I by 4 pi So, dl cross S, which is dl S cos alpha divided by S cube. So, I have I leave one S and the remaining I write as r square plus z square. So, this S cancels off and I have essentially mu naught I by 4 pi dl cos alpha by r square plus z square, and dl is nothing but, let me write it as dz, because dl is nothing but a small current element along the z direction. So, I replace dl by dz. So, the total magnetic field will be obtained by integrating this vector. So, B magnitude total will be equal to mu naught I by 4 pi integral dz cos alpha divided by r square plus z square from z1 to z2. Z1 is the coordinate of the bottom point of this element, Z2 is the top coordinate. So, from Z1 to Z2 if I integrate, I will get this. Now, I can use a small change of variables. So, Z is equal to, if I write Z is equal to r tan alpha, you can see here Z is this distance, r is this distance, alpha is this angle. So, Z by r is tan alpha. So, Z is equal to r tan alpha. So, and dz will be equal to r secant square alpha d alpha, and r square plus z square is nothing but r square into 1 plus tan square alpha, which is equal to r square secant square alpha. So, magnetic field vector magnitude is mu naught I by 4 pi integral. So, dz is r secant square alpha d alpha cos alpha by r square secant square alpha. So, secant square alpha cancels off and I get mu naught I by 4 pi r integral cos alpha d alpha, which is equal to mu naught I by 4 pi r sin alpha 2 minus sin alpha 1, where alpha 1 and alpha 2 are the limits. And so, let me write here. So, alpha 1 is this angle and alpha 2 is this angle. So, alpha 2 is this angle where the top portion of the element subtended at this point, and alpha 1 is the angle subtended by the bottom portion of the current element with the horizontal line at this point P. And I can from here I can immediately write the values of sin alpha 1 and sin alpha 2 in terms of Z1 and Z2. So, you can see here sin alpha 1 is this Z1 divided by this distance, and sin alpha 2 is Z2 divided by this distance. So, I can also write this equation in a slightly different form. So, magnitude B vector, which is equal to mu naught I by 4 pi r into Z2 by square root of Z2 square plus r square minus Z1 by square root of Z1 square plus r1 r square. So, I have just replaced sin alpha 2 by Z2 by square root of Z2 square plus r square, and sin alpha 1 by Z1 by square root of Z1 square plus r square. So, that is the magnetic field produced at this point. So, the field at the point where I am interested depends on the coordinate Z1 and Z2 and essentially these angles, and that is a nice expression which is useful whenever I need to have calculate magnetic field by straight segments of current elements, and for each straight segment, if I know the coordinates of the two ends, I can use that to calculate the magnetic field. Now, I want to use this expression to solve another problem, which is the following. A length L of wire carrying a current I is to be bent into a circle or a square each of one turn. In which case will the magnetic field at the center be greater. That means, from a given length I make a square, and for the same length I make a circle, and at the center I want to calculate the magnetic field. The length of this square is the same as the length of the circle, and if I flow a current, I need to calculate the magnetic field at the center here and center here and compare the two magnetic fields. So, I want to solve this problem. Now, please note, in the square case, if I draw the square here, I have to calculate the magnetic field here. So, if I need to calculate the magnetic field here, suppose I draw the lines here, this is the current flowing. So, this is a problem which is very similar to what we had before. So, the total magnetic field at this point consists of magnetic field produced by this current element plus the magnetic field produced by this current element plus the magnetic field produced by this current element plus the magnetic field produced by this current element. We have already seen the magnetic field produced by one current element, and also remember that all current elements produce magnetic fields in the same direction. So, they are all the magnetic fields are coming up from here. So, you see the current is flowing like this. So, the magnetic field is coming up here, this current also produces magnetic field coming up. So, all the magnetic fields produced by all the four current elements are in the same direction. So, I can calculate the total magnetic field by simply adding the magnitudes of the magnetic field produced by each of them. Now, if you look one of the current elements, if I look at this current element, because the total length is L of the wire, each side has a length L by 4. So, this is an L by 4 length, and if I draw the perpendicular, so this is this distance is L by 8, and this being the center, this is also L by 8. So, if you recall, we had just obtained this formula mu naught I by 4 pi r into Z2 by square root of Z2 square plus r square minus Z1 by square root of Z1 square plus r square. So, for this current element, Z1 is equal to minus L by 8. Look at this is the perpendicular drawn here. This is minus Z by 8, minus L by 8, and Z2 is equal to plus L by 8. This is the coordinate of this point, and r is equal to L by 8, because that is this distance. So, this distance is L by 8, this is L by 8, this is L by 8. So, if I want to calculate now Z2 by square root of Z2 square plus r square, which is equal to L by 8 by L by 8 into square root 2, which is equal to 1 by square root of 2. Z1 by square root of Z1 square plus r square is equal to minus L by 8 by L by 8 times square root 2, which is equal to minus 1 by square root of 2. So, the total magnetic field, because of one current element, magnetic field due to one side of the square will be equal to mu naught I by 4 pi into L by 8. Remember, r is here, that is L by 8, and then I have 1 by root 2 plus 1 by root 2, which is equal to 2 mu naught I by pi L into root 2. So, this is 2 by root 2, which is root 2, and I have 2 mu naught I by pi L into root 2. So, the total magnetic field is 4 times this, 4 into 2 mu naught I by pi L root 2, which is equal to 8 square root of 2 mu naught I by pi L. So, let me call this B square. So, that is the magnetic field produced by the square. L is the total length of the wire which is producing this magnetic field. So, the square current carrying square produces a magnetic field at the center given by this, and which I have calculated by summing up the magnetic field produced by each of the current elements. Now, I want to find out what is the magnetic field produced by circle. So, that is my wire put in the circular form, and if the radius is r, the total length is L, which is equal to 2 pi r. So, the radius of the circle will be L by 2 pi. Now, to calculate the magnetic field here, I use again I can very simply use Biot-Savart law. So, here it is, so I take a current element. So, this is d phi and this angle is phi. So, this is r d phi and the current is flowing like this. So, I can write dB. So, the current is flowing like this. This is the S vector here. So, you can see here this line dl is always perpendicular to this S vector r vector here, and so I will get dB is equal to mu naught I by 4 pi into I into the length dl cross r. So, dl is r d phi by r square. So, dl cross r by r cube. So, one of the r cancels off. So, I will essentially get mu naught I d phi by 4 pi r. So, the total magnetic field will be equal to mu naught I by 4 pi r integral d phi from 0 to 2 pi, which will give me mu naught I by 2 r, and I can replace r in terms of L by 2 pi. So, I get mu naught I by 2 r is nothing but L by pi. So, mu naught I pi by L. So, if I call this circle, so B circle is equal to mu naught I pi by L. So, I have taken the same length of wire, one put in the form of a square, one wire put in the form of a square of length L, and the same wire I have been into a circle, and I find these two magnetic fields. So, let me write these two fields here. So, for the square B s was equal to 8 square root of 2 mu naught I by pi L, and B for the circle of the same length is mu naught I pi by L. So, the ratio B square by B circle will be equal to 8 square root of 2 mu naught I pi L divided by mu naught I pi by L, and that is equal to, so I cancels off, mu cancels off here, and L cancels off. So, I get 8 square root of 2 by pi square, which is approximately 1.15. So, if you take a certain length of wire and put it in the form of a square or in the form of a circle, the magnetic field at the center of the square will be larger by a factor of 1.15 compared to the magnetic field produced at the same point if the wire was bent into the form of a circle. So, you have seen here how to use the Biot-Savart law to calculate the current element magnetic field produced by current element, and use that to calculate the magnetic field produced by wire structures consisting of multiple current elements. So, if you are given, for example, an n-sided polygon with straight current elements, you can actually calculate the magnetic field produced by each of those elements, add them up. But please remember, magnetic fields are vector quantities, and you have to ensure that all the fields you add are done in vector addition. Let me go to another problem, another interesting problem here. If a finite wire is used to wind 6 turns, around an insulating sphere of radius a, such that each turn makes an angle of 30 degrees with the adjacent turn, and that all the turns intersect at diametrically opposite points on the surface of the sphere. I will draw a figure to explain this a little more carefully. If a current I is passed through these turns, find the magnitude of the magnetic field at the center of the sphere. So, let me draw a figure to explain this problem. A finite wire is used to wind 6 turns around an insulating sphere. So, I take an insulating sphere of radius a and I wind turns like this. So, I have one winding which goes like this, the next winding comes here. So, this angle is 30 degrees, then another winding comes here at 60 degrees, another winding comes here at 90 degrees, then another winding comes here at 120 degrees and another winding comes here at 150 degrees. So, there are 6 windings. So, each of them is carrying current. So, here there are current flowing like this. So, I have 6 windings, each of them rotated by 30 degrees. So, this is horizontal, next 30 degrees, 60 degrees, 90 degrees, 120 degrees, 150 degrees, and then you have the original one which is at 180 degrees. So, the problem is to calculate the magnitude of the magnetic field at the center. Now, what is actually happening is, for example, the horizontal winding will produce a magnetic field like this at the center. The next winding, which is at 30 degrees, will produce a magnetic field at the same point slightly inclined. Because the two windings have the same radius, they will produce the same magnetic field, but inclined now by 30 degrees. The next one, which is at 60 degrees, will produce one inclined at 60 degrees. The fourth one will be at 90 degrees, it produces like this. Then the one which is at 120 degrees produces like this. Then the one which is at 150 degrees will produce like this. So, you have 6 turns, each of them producing a magnetic field which is slightly oriented with respect to these the earlier magnetic fields. So, what you need to do is to calculate the total magnetic field, the sum of the magnetic fields of all this, and we have to remember, as I mentioned, that magnetic field is a vector quantity and I must use vectorially. So, let me draw the vectors. So, you will have one magnetic field like this, next one 30 degrees, next one is 60 degrees, next one is 90 degrees, then 120, 150. So, these are the 6 magnetic fields produced. So, I can actually calculate the magnetic field along the vertical directions and the magnetic field along the horizontal direction, and from those two I can add up the total magnetic field I can calculate. So, now let me first calculate component of magnetic field along the vertical direction. Now, for this of course, I need to know what is the magnetic field produced by a current loop of radius a at the center, and that magnetic field happens to be B is equal to mu naught I by 2a. We just now calculated in the earlier problem the magnetic field produced by a current element like current, a circular loop of current will be like this, and it is pointing perpendicular to the plane of the circular loop, and it has a magnitude mu naught I by 2a at the center. So, each of these loops produces a magnetic field of magnitude mu naught I by 2a at different orientations. So, I need to calculate. So, this is 30 degrees, this is another 30 degrees, this is 30 degrees, this is 30 degrees, and this is 30 degrees. So, what is the vertical component? B vertical. So, the first one is mu naught I by 2a plus the second one, the magnitude of this vector is mu naught I by 2a, its vertical component is cos 30. The next one, the magnitude is mu naught I by 2a, the component is cos 60 degrees. The fourth one, mu naught I by 2a cos 90 degrees plus mu naught I by 2a cos 120 degrees plus mu naught I by 2a cos 150 degrees. 1, 2, 3, 4, 5, 6. 6 coils produce different magnetic fields. This is the vertical component of each of the magnetic field, which I can add up, and this happens to be mu naught I by 2a into this is 1 plus cos 30 is root 3 by 2 plus cos 60 is half, cos 90 is 0, cos 120 is minus half, and cos 150 is minus root 3 by 2, and this happens to be equal to mu naught I by 2a. So, what is actually happening is the vertical component of this field is cancelling the vertical component of this field, the vertical component of this field is cancelling vertical component of this field, there is no vertical component of this. So, the total vertical component is nothing but the magnetic field produced by the horizontal coil, which is essentially vertical, and it is mu naught I by 2a. I can similarly calculate the horizontal component of magnetic field along the horizontal direction. So, BH, now instead of cosine I will have sine functions, horizontal components are all sine. So, I will have mu naught I by 2a so sine 0 plus mu naught I by 2a sine 30 degrees plus mu naught I by 2a sine 60 plus mu naught I by 2a sine 90 plus mu naught I by 2a sine 120 degrees plus mu naught I by 2a sine 150, and you can simplify this. This is mu naught I by 2a into 0 plus half plus root 3 by 2 plus 1 plus root 3 by 2 plus half. So, sine 0 is 0, this is half, this is root 3 by 2, this is 1, this is root 3 by 2, and that is half, which is equal to mu naught I by 2a into 2 plus root 3. So, horizontal component is this one. We have already calculated the vertical component as mu naught I by 2a. So, we can calculate the total magnetic field magnitude. So, B magnitude is equal to B vertical square plus B horizontal square root, which is equal to mu naught I by 2a into 1 plus 2 plus root 3 whole square whole raised power half, and that comes out to be about 1.93 mu naught I by a. So, in this problem, if you have these kind of windings, 6 windings at each inclined by 30 degrees, you can actually calculate the total magnetic field at the center of the sphere, and that happens to be about 1.93 times mu naught I by a. So, this problem tells me that I can actually use the magnetic field produced by small current elements, and here it was a circle, and I must be careful in calculating the total magnetic field, because magnetic fields are vector quantities, and when I add the vector quantities I have to be a little careful. Okay. Now, let me go to another interesting problem. A long solid conducting cylinder of radius r has a cylindrical hole of radius a drilled out such that the axis of the hole is parallel to the axis of the cylinder. If B is the distance between the two axes and a current I is passing through the remaining solid cylinder, show that the magnetic field is constant throughout the hole. So, the problem is essentially like this. I have a solid conductor, cylindrical conductor, and I have a hole drilled out. So, the conductor now has only only the conductor now, and so this is the hole, and this hole axis is parallel to the axis of the cylinder, and this distance is given as B, and a current I is passing through this entire structure. I need to calculate the magnetic field inside this hole and show that it remains constant. Okay. So, first thing is, so let me draw the figure again here. So, I need to take a point here, so that is the center. So, please remember there are so the conductor is only this part is only the conductor. Now, the problem to calculate the magnetic field like this may become complicated, but I can use a very simple procedure which involves superposition. So, what I can do is I calculate the magnetic field produced by a completely solid cylinder without the hole. I calculate the magnetic field produced by a cylinder of this diameter of this size at the same point, and then subtract the two. So, I first calculate the magnetic field at this point because of the solid cylinder without the hole, Then I calculate this magnetic field at the same point because of a cylinder of this radius at the same point, and then subtract the second magnetic field from the first magnetic field to get the magnetic field at this point because of this the cylinder with the hole. So, that is the procedure we are going to do. So, for this first let me calculate the current density. So, current density J is equal to current I is flowing through the entire area of this conductor, which is now pi r square minus a square. So, pi r square is the area of the cylinder, pi a square is the cylinder is the radius of the hole. So, pi r square minus a square is the effective area through which the current is flowing, and so the current density is I by pi r square minus a square. So, now I am going to calculate what is the magnetic field produced at this point due to a solid conductor carrying this current density. I will calculate then the magnetic field at this point due to a conductor of radius a carrying a current density J, subtract the second one from the first and calculate the total magnetic field, always keeping track that magnetic field is a vector quantity. So, first things, so magnetic field due to solid conductor without the hole of radius r. So, I need to calculate the so this distance. So, this distance let me take it as r. So, we can so this is now, so the problem is essentially I have a solid conductor of radius r and I take a point at distance r from here, and the current is flowing parallel to the axis of the wire. So, the magnetic field will be in this azimuthal direction. So, I can actually use Ampere's law. So, I can use this law, integral B dot dl is equal to mu 0 I enclosed. So, because the magnetic field is azimuthal as we have done before, B dot dl just gives me 2 pi r times B is equal to mu naught I enclosed will be J times pi r square. Pi r square is the area and the enclosed current is this thing. So, B is equal to the magnitude of B will be equal to mu naught J r by 2. Now, at this point the magnetic field will be directed like this. So, let me call this, so in this figure this is the normal. So, let me call this N1. So, I can write the magnetic field vector as mu naught J r by 2 N1 cap. So, that is the magnetic field produced by a solid conductor of radius capital R at a distance small r from the center. Now, I must calculate what is the magnetic field produced by a cylinder of radius a. So, let me draw the same figure. So, this was the bigger cylinder of radius r and I am now, so this is the center. Now, I take a cylinder of this radius a and calculate the magnetic field at the same point. So, magnetic field due to solid cylinder of radius a at a distance s from its center. So, this distance I am going to assume is s. So, if I go back to the original figure, I have called this distance as r, this distance is s. Please remember r is the distance of this point where I am calculating the magnetic field from the axis of the big conductor, s is the distance of that point from the axis of the hole, and I am now calculating what is the field produced at this point at a distance s from the axis of a conductor of radius a. So, just like before I can draw a an Amperian loop like this and use this formula B dot dl is equal to mu 0 I enclosed. So, 2 pi s into B will be equal to mu naught j into pi s square. So, B will be equal to mu naught j s by 2, and now the normal will be in this direction. So, if I go back to the original figure here, this normal N 2 will be like this. The magnetic field produced by the thick conductor is in this direction. At the same point, the magnetic field produced by a conductor of radius a carrying current in the same direction is in this direction, which I am calling as N 2. So, let me call this B 2 is equal to mu naught vector mu naught j s by 2 into N 2 cap. Now, let me draw a figure here to explain better. So, this is x y axis. So, this is the point where I am trying to calculate. This distance is r and this distance is s. Okay, so, this is the perpendicular here. So, I have the magnetic field produced by the big conductor is along this direction, and the magnetic field produced by the other the hole with the conductor corresponding to the hole is actually in this direction. So, let me draw minus N 2 cap, and I call this angle theta and this angle phi. So, this line is perpendicular to this line, and this line is perpendicular to this line. So, this angle is also theta. This line is perpendicular to this line, this is the normal, and this line is perpendicular to this line. So, this is phi. So, total magnetic field B is equal to I should have named this as, let me call this B 1, that is due to the thick conductor of radius capital R. So, B is equal to B 1 minus B 2. Please remember, what I have done is B 1 is the field produced by the thick conductor without the hole, B 2 is the field produced by the smaller conductor here of radius a at the same point. So, if I remove this conductor, I have to remove the component of magnetic field produced by that portion of the conductor, which is B 2. So, B 1 minus B 2 is my magnetic field produced at this point. So, which is nothing but mu naught j by 2 into, now B 1 is R n 1 cap minus B 2 has S n 2 cap minus S n 2 cap. So, the total magnetic field is, this is the magnetic field produced by the solid conductor without the hole, this is the magnetic field produced by a conductor of radius a corresponding to the hole. So, if I remove that component, that magnetic field portion, I will get the magnetic field produced by the conductor with the hole. So, now let me write in terms of components. So, this is mu 0 j by 2, now R times n 1 cap. So, if you look at n 1 cap, it has a x component and a y component. So, the x component is minus sin theta I cap plus cos theta j cap. This vector has a component along this direction, x component, which is negative. So, minus sin theta I cap plus a positive component along y, which is plus cos theta j cap, and then minus s times n 2 cap. So, because I am writing this is minus n 2, so I have a plus sign here. So, this will be plus s into, so you will have sin phi I cap plus cos phi j cap. This is n 1 cap, this is minus n 2 cap. So, I have taken the minus sign, minus n 2 cap I have written. So, this is nothing but equal to mu naught j by 2 into I cap into minus r sin theta plus s sin phi plus j cap into r cos theta plus s cos phi. Okay, so I have combined the I cap terms and the j cap terms and I get these two. So, you can see here r sin theta, this is also theta. So, r sin theta is this length and s sin phi is also this length. So, these two cancel off, r cos theta is this distance, s cos phi is this distance. So, r cos theta plus s cos phi is the distance from here to here, which is nothing but b, the distance of the center of the hole from the center of the axis of the conductor. So, I get a very interesting expression that b is equal to mu naught I mu naught j b by 2 to j cap, which if I write in terms of current mu naught I b by 2 pi r square minus a square to j cap. So, that is the magnetic field produced by the conductor, and there is a hole here and inside the hole. So, the conductor is carrying current like this, that is a hole. So, the magnetic field inside at any point is given by this, and as you can see here it is a constant all along the y direction. So, this y is defined here. Okay. Now, let me come to a last problem involving electromagnetic waves. The electric field of a plane electromagnetic wave propagating in free space is given by E is equal to 10 I cap plus 15 j cap sin 4 pi 10 to the power 6 into C t minus z volts per meter. C is the speed of light in free space, and z is in meters. So, what is the wavelength of the wave? What is the wavelength of the wave? And calculate the corresponding magnetic field. So, let me give you the answers. I would like you to work it out. Please remember, electromagnetic fields, you have to find out what direction is the wave is propagating, and so let me give you the answers. So, the wavelength is 0.5 micrometers and the B field will be given by 15 I minus 10 j by C sin 4 pi 10 to the power 6 into t minus. So, that is the magnetic field. So, we will stop here. So, what we have done today is to discuss some problems in magnetic fields, and which has exposed how we can employ techniques like Biot-Savart's law or Ampere's law to calculate fields produced by various configurations. And I hope with the understanding of basic concepts in electromagnetics, you will be able to solve many problems in your career. Thank you very much.